You've seen it in the movies a million times, right? A giant rock just hurtling through space, dead set on a collision course with Earth. Well, it turns out this isn't just science fiction. It's a real, if pretty rare, threat that scientists are taking very seriously. So, what are we actually up against, and do we really stand a chance? To even begin to talk about the solutions, we have to wrap our heads around the terrifying scale of the problem. And I mean, forget what you've seen in the movies. The reality of a major asteroid strike on a modern city, well, it's a cascade of destructive events all happening at pretty much the same time. And this quote, this isn't from a sci-fi novel. It's from a super detailed scientific model of what would happen. See, an impact doesn't just dig a big hole in the ground. No, it unleashes this trifecta of devastation on a scale that's just, it's hard to even imagine. And it all kicks off the second it hits. So, what is it that makes these things so catastrophic? Well, it really comes down to three main forces that just blast out from the impact site. We're talking intense heat, ground-shattering shockwaves, and a totally devastating air blast. Let's break those down. Okay, so the very instant that asteroid hits, it vaporizes, creating a fireball literally hotter than the surface of the sun. But this isn't just some explosion you can see. It's a massive, silent pulse of thermal energy radiating outwards at the speed of light. Now, look at this graph, because this is where the sheer scale of it all becomes terrifyingly clear. It shows how far that heat from a big impact travels. See those lines for first-degree burns and clothing ignites? An impact somewhere near Los Angeles could pump out enough heat to cause third-degree burns and set clothes on fire all the way down in San Diego. That's 200 kilometers away. Just incredible. At the exact same time as that heat flash, the impact dumps an unimaginable amount of energy straight into the Earth's crust. This kicks off seismic waves, basically creating an earthquake that would be at the absolute top of the intensity scale. We're talking damage so severe that most buildings are just destroyed, foundations are torn up, and the ground itself literally cracks open. And then finally, there's the air blast. The impact shoves the atmosphere out of the way, creating a superheated pressure wave that expands faster than sound. It's immediately followed by winds that could top 150 meters per second. That's strong enough to flatten just about any building that survived the earthquake. It's just a complete layered catastrophe. So yeah, after hearing all that, the big takeaway is pretty simple. The absolute best way to survive an asteroid impact is to make sure it never, ever happens. And you know what? That's not just wishful thinking. It's an active, coordinated global effort with a really cool name, Planetary Defense. Planetary defense isn't just one thing. It's not like you just build a weapon and you're done. This diagram illustrates it perfectly. It's a constant cycle. We search the skies. We track what we find. We characterize the objects to figure out what they're made of and how big of a threat they are. And then we coordinate a plan to mitigate the danger. It's a whole system for protecting the planet. Here is the official definition, and it's important. It covers the whole shebang. Everything from finding the asteroids in the first place, to developing the tech to actually stop them, all the way to creating emergency plans for what we do if an impact just became unavoidable. And this slide right here shows you exactly why this effort is so urgent. Take a look at that 140-meter category. Those are what we call the city killers. They're big enough for regional devastation, and there are an estimated 25,000 of them out there. Now, here's the really alarming number. We've only discovered about 40% of them. That is a huge blind spot. So let's say we find one of these asteroids and it's on a collision course. What do we actually do? Well, the strategy is surprisingly straightforward, even if pulling it off is incredibly complex. It all boils down to these three steps. First, you gotta find them. That means constantly, systematically scanning the skies. Then you characterize the threat. Is it a solid chunk of rock or more like a loose pile of rubble? That detail is absolutely crucial. And finally, you mitigate. That's when you take action. And that first step, find and track, is about to get a massive upgrade. We've already got powerful survey telescopes like Pan-STARRS doing the work, but soon the Vera C. Rubin Observatory in Chile is coming online. This thing is designed to survey almost half the sky every few nights. It's going to dramatically crank up our discovery rate. Now, when we talk about mitigation, the goal is not to blow the asteroid into a million pieces like you see in the movies. I mean, think about it. That could just create a bunch of smaller impact threats instead of one big one. The goal is way more elegant. Just give it a tiny nudge, years in advance, to change its orbit just enough so that it misses Earth entirely. And in 2022, we proved we could actually do it. This right here is the final image from NASA's DART spacecraft. That stands for the Double Asteroid Redirection Test. Its target was that little moonlet Dimorphos. The mission was a spectacular success, and it was the very first time humanity has ever purposefully changed the motion of a celestial object. So, how well did it work? Well, the impact changed Dimorphos's 12-hour orbit by a full 33 minutes. Now that might sound like a tiny nudge, but it was definitive proof that this kinetic impactor technique is a real, viable way to defend our planet. For the first time, humanity proved it has the power to rearrange the solar system, just a little bit. But, the success of DART wasn't an ending. Far from it. It was really the beginning of a whole new era in planetary defense. So let's take a look at what the future holds. Our ability to actually see these threats is about to take a giant leap forward. Along with that amazing Rubin Observatory, NASA is developing the NEO Surveyor Space Telescope. It's going to be positioned out in space to spot asteroids that are tough to see from Earth. And on top of all that, international cooperation through networks like the IAWN is stronger than it's ever been. And this chart just brilliantly illustrates the impact these new tools are going to have. That gray line shows our current progress in finding these potentially hazardous asteroids. But look what happens when Rubin and NEO Surveyor come online. We are going to see a massive acceleration, pushing us toward that big goal of finding 90% of these things. We also have a pretty unique dress rehearsal coming up. In 2029, a really big asteroid named Apophis is going to fly past Earth, closer than some of our own satellites. Now, don't worry, it poses zero threat, but it's an incredible scientific opportunity to study one of these potentially hazardous objects up close and really test our international tracking and coordination. So at the end of the day, here's where we are. The DART mission gave us the answer to a huge question. Yes, we can protect ourselves, but the technology to deflect an asteroid is only useful if we have enough warning. The ultimate challenge of planetary defense isn't really about might, it's about sight. It's about finding that city killer out there in the dark before it finds us.